Why is it?
What?
The white screen, the screen.
Yeah, this one. Thank you. So we have manifolds. We said, okay, at any point we have these local charts, phi and phi inverse for a flat space. We defined curves, right? What do you mean by a curve? So it's a map from an interval in the real line to the manifold. So as t, your coordinate here, changes, the points on the manifold change. This is gamma of t, your curve. We define what do we mean by a differentiable function f that takes a point on the manifold to the real line. We defined the tangent space and tangent vector. We spent quite a bit of time with tangent space. And please, if you have a question about any of these, stop me. We said that this is a vector space. It's isomorphic to Rn actually. We can add and multiply by scalar vectors in the tangent space. So this is TPM tangent space at a point. We also defined the derivations, that set of, you can say, differentiation that takes C infinity functions and gives you a real number dp of m, and we actually stated that they are equal. These two guys are equal. So any vector, any tangent vector, any velocity vector is a derivation, and any derivation is a velocity vector, comes from a velocity vector. That was a very important finding, as we're gonna stress today as well. What else? We defined tangent or push forwards, right? How we're gonna move or transfer velocity vectors. It's just by the push forward or tangent map. This is just Jacobian. And last time we defined the tangent bundle, Tm, right? It's actually a manifold itself with dimension 2n, obviously. Okay? Because it's locally can be defined as product of open subset of the manifold cross Rn. Rn is already a manifold, and the open subset of a manifold is a manifold. So you can easily establish a manifold structure, and it's double the dimension. This is what we had until last time. And today we will talk in more detail about vector fields. You have seen the lecture, I assume. We will, have some repetition, little bit, but we'll focus on something else. And even if you didn't watch the lecture, please feel free to come up with questions. So a vector field, it takes a point and gives you a vector in the tangent space on the point, obviously. So at any point, it gives you a vector in the tangent space. At any point, it gives you a vector in the tangent space, and so on. So it looks like the flow field, right? The field, the velocity field of a flow. At any point, it gives you an arrow, like here's a vector field, vector value function, so x, y, x squared plus y squared, y, z, whatever. This is a vector field on R3, right? It is a vector field on the sphere, y negative x 0. This is the one that we usually give as an example. So this is actually in R3. We should write it in coordinates of the sphere, but writing it in R3 is even more interesting because it shows you how it's always tangent. When even writing it in the ambient space, how it gives a vector that is always tangent to the sphere. Okay?
Professor?
Yes?
Why is the dimension of the tangent bundle is 2n?
Because the tangent bundle is the set of points and velocities. So points already are dimension n, and velocities are dimension n. So together dimension 2n. It's like I said in mechanics, usually we have Q, the set of all positions, So the tangent bundle will be every q and the q dot,
Oh,
right? The state space. So this is positions, this is position and velocity.
Professor.
Yeah.
Yeah, I have a question. So, we're assuming that the tangent space always has the same dimension as the manifold, right? But sometimes it drops, right?
It doesn't drop. I mean, for a smooth manifold, no, it doesn't drop. For a smooth manifold, the tangent space is always the same and it's isomorphic to Rn. Okay. Yeah. If you have if your manifold is not smooth, then it's a different story. Okay, so this is a vector field on S2, right, on the sphere. It always gives you a tangent point to the sphere. So this in terms of terminology and language, we will denote the set of all vector fields the set of all vector fields on M, we will denote it by this thing. In dynamics, I denoted by gamma of M, but then I realized gamma will have some confusion with Christoffel symbol, so let's have this guy. So we are saying that the vector field gives you a vector, a velocity vector at each point, right? A velocity vector at each point, a velocity vector at each point. And we already have seen last time that the velocity vector in the tangent space, this is the velocity of some differentiable curve, right? So here we have this velocity is the velocity of some differentiable curve, the same here, the same there. So let's connect them and have what we called, this would be what, like 8, right? And what we call the integral curve. So given vector field, right? So it's in chi-m, and given a point on the manifold, then gamma defined from some interval subset in the real line into M, satisfying or with gamma of 0 is P. And what do you mean by an integral curve? We're saying that this velocity of the vector field is the velocity of the curve at this point, and the same at this point, at that point. So the velocity of the curve is gamma prime of t, right? This is the velocity of the curve. This is equal to the velocity dictated by the vector field. The vector field gives you a different velocity at different points. So at what point this? This is at the point of gamma, right? So, and this is what we write as gamma v composed with gamma, right? And this is for all t in I. So this is the definition of an integral curve, okay? And it's called an integral curve of v at p. Okay, let's start with the point B. In coordinates, if you like to write this guy in coordinates, what do you mean in coordinates? So this guy is here, now we have the curve, sorry, here is the curve, gamma, we have our coordinates, right? So this is the local chart. So these coordinates, the curve in the coordinates, which is phi composed with gamma, is actually x1 up to xn, right? So in coordinates, this gamma prime is x1 dot xn dot as a function of time. This is equal to, like I said, v in coordinates is a vector valued function. So this is v1 function of x's coordinates up to vn and we know that at time 0, so all the x's, I'll give an array, and time 0 is the point P, right? So you can see here that vector fields represent different, this is an ODE, right? So this is an ODE. So vector fields actually represent differential equations of manifolds. In other words, the integral curves are obtained by solving differential equations. Okay? So this is why whenever we have a differential equation, we can think of the right-hand side as a vector field acting on an F. Okay? This language is pretty common actually. But here you see where it comes from. So when we solve this differential equation, you get the integral curve. And are we sure about existence? Because yes, I can have here, I can have at this point, I can have a velocity, I have a velocity vector, so I can have a curve whose velocity vector matches this velocity vector. In the very next point, I can have another curve, but are we sure that we can patch all these curves into one smooth curve? Okay? So are we sure that there exists this integral curve? Solution for this differential equation, in other words. If you form it into existence of solution differential equations, yeah, we know this very well, and you should study it in much more detail in 275, but we know if we have continuity, right? If you have a continuous right-hand side, the vector field continuous, we are sure of existence. And if we have locally Lipschitz, right? Lipschitz continuity, then we are guaranteed uniqueness, right? And if it's globally Lipschitz, we are guaranteed uniqueness for all time, existence and uniqueness for all time. So locally Lipschitz is existence and uniqueness for some time. So yeah, we have this result, of course, because our vector field is smooth. So we'll guarantee Lipschitz continuity. So given V as a vector field, P and M, there exists an interval, open interval, that includes 0 and a unique gamma. It's a curve from this open interval to M such that gamma of 0 is P and gamma satisfies the property of an integral curve, right? Which is, let's have it as a star. Here is a star. Okay? So we'll guarantee this guy. And if this open interval is everything, so if this guy is just negative infinity to infinity, we call this complete vector field, right? That has a solution, integral curve defined for all time, not just for it doesn't have finite state. So, and we know, I mean, if you recall again from concepts and nonlinear systems, you know that any vector field on a compact manifold is complete. The manifold actually doesn't have to be compact, but the vector field, the support of the vector field, the definition of the vector field, or the support of the vector field has to be defined on a compact set in the manifold. So if the manifold itself is compact, that's good. So we're guaranteed existence and uniqueness, so that's good. Any question about that so far? Any question? Any question? Please don't feel shy. If you have a question, let's come up with it. Let's have a discussion about it. So right here, there is nothing new. It's just differential equations. I'm just giving it a little bit different language.
So, Professor, can we have some examples on compact and non-compact manifolds?
I mean, S1 is compact manifold. R is not compact manifold. Right? R.
Okay, so
Yeah,
we
so
open-
x dot equals x squared. This is a vector field, right, defined on R. Okay? R is not a compact manifold. This guy, the solution is what? If you start with x of 0 is 1, you get 1 over 1 minus t, so it has a finite skip time. At t equals 1, this will blow up. So it doesn't have a solution for all time, because it's undefined on a compact manifold. If you say, okay, it's x dot equals x squared on 0, 1, and 0 outside of this compact set, then yeah, you'll have a solution for all time. It will not blow up.
Professor, what is this Lec06?
Lipschitz. Lipschitz, so say 1D, okay? So you have the distance between f of x and f of y is this then some constant times the distance between x and y. So you can visualize it as this is f, this is x, okay? This constant will set some boundaries here. So your function can do anything here, but it cannot come within this guy, which means, so this is locally Lipschitz around 0. So which means that the function cannot have a very steep derivative. It has a very steep derivative, then it fails the Lipschitz property, okay? It has to be nice enough. So this is one of the nice properties, right? So you have continuity, then Lipschitz continuity is a high requirement, differentiable is a high requirement, and so on and so forth. So if it's differentiable, then of course it's Lipschitz. So, what did we cover so far? Okay, so we covered the integral curves. Now let's, the solution of a differential equation, this differential equation, it depends on time, right? And also depends on the initial condition, correct? So the curve, the integral curve at a point P, we're fixing the initial condition and varying time. We'll do the other way around, and it will give us a nice definition, an important definition, so this will be 9. The flow map. So given a vector field V, we define this flow map by TV. So here we're viewing it, we're fixing T and varying the initial condition. So it takes a point on the manifold and gives you, this is how we read it, the flow along the vector field